Alright, it has been a minute since I last uploaded, but I'm going to try and upload a little bit more regularly, doing these mini practice problems, and hopefully it's not going to take too much time, and I'll be able to upload faster. So, let's just get right into it. A ball with a horizontal speed of 1 meter per second rolls off a table 1.25 meters tall. How far from a point on the floor directly below the edge of the bench will the ball land? Okay, so let's just highlight some key information. Okay, so first, horizontal speed, that's important, 1 meters per second, and the table it rolls off is 1.25 meters tall. We are trying to determine how far from a point on the floor directly below the edge of the bench will the ball land. So how far, basically. If it's still confusing, hopefully this diagram will clear up some confusion. So let's say this is our table right here. Okay, let's say that's like the leg of the table, and this is the sort of the surface of the table, and we have our ball, just like that. Here's our ball, okay? And it is going to go rolling off this table at a speed of 1.0 meters per second, okay? Horizontal speed, okay, so we know that this is not some combination of horizontal and vertical. It's not a complex vector, it's just a horizontal vector, okay? And this table right here is 1.25 meters tall, okay? And basically what we're trying to find is the distance from here, which is when the ball starts to fall off, okay, to, actually hold on, let me redraw that. Falling off the table to however far it takes until it hits the ground, okay? So how we're going to approach this 2D kinematic problem is to sort of assess what we know already and go from there. So in a 2D kinematic problem, you're going to set up your x's, so let me get rid of that, which are just indications of position. So movement along the x-axis is indicated by these x variables. So x naught is going to be the initial x position. X is just going to be the final position. We also need a v naught in the x direction. So the velocity at the beginning in the x direction. We need velocity at the end in the x direction. We need acceleration in the x direction. And we need time. Okay, there's no such thing as time in one direction versus another, so it's just time. We also, actually let's fill these in. Okay, so this here is our initial position, so this is x naught, and for ease of computations, I guess we can just say this is 0 meters. Okay, essentially what we're trying to find then is this right here, x. How far does it go? So that's the question. V naught x is 1.0 meters per second, and this is sort of just something you've got to know, but when you have an object in in this case that has a horizontal velocity, that portion is going to stay constant, okay, assuming there's no air resistance. Okay, because there is no change in the velocity, the acceleration is 0 meters per second squared, and the time, we don't know how long it takes for the ball to fall. Okay, so that's what we know about the x's. Now we go to the y's, because the y's will also help us hopefully find this x right here. Okay, so we're just going to set up the problem in a similar manner. Okay, and okay, so this is where things can get tricky, because I'm actually going to start with the acceleration in the y direction. The ball always has gravity acting on it. So its acceleration in the y direction is always 9.8 meters per second. But this is where things can get tricky because you have to make sure that the sign over here is consistent with what you're actually saying. So what do I mean by that? Well, if I say that this ball is accelerating 9.8 meters per second, I want to say that the ball is accelerating this way, 9.8 meters per second, right? Because, balls don't suddenly fly upwards, okay? So it's important to note that this direction, if we're going to say that it's accelerating positive 9.8 meters per second this direction, that this direction is positive, okay? Meaning this would be like 0, this would be towards the positive end, this would be towards the negative end, if we were to think of this as like a number line, okay? So why is this important? Because that fundamentally influences what we set as y naught and y, okay? Since y naught is always obviously going to be 0, okay, it's actually, let me take that back. It's not always obviously 0. Because this direction is positive, we want to make sure that the y distance, in other words delta y, change in y, is positive. And in order to make that positive, we need to set y naught equal to 0 and y to 1.25 meters. Okay, so what that would look like is y naught would be here and y would be here. With y naught set up here and y over here, it's consistent with what we've set for acceleration. We said that acceleration is 9.8 meters per second this way, and we said that it was positive. Likewise, that should be consistent with the change in position. So this should be 0, and it should be going towards the positive direction. Okay, so the velocity initially in the y direction is 0 meters per second, and the velocity in the y direction, the final velocity in the y direction is something that we do not know, and the time we also don't know. Okay, so with these values, what can we do and what can we solve? Well, okay, I'm kind of running out of space. Let's see what we can do. Okay, well, I'm just gonna I'm gonna see if I can open a new one. Whoa. Okay, let me change this. And instead of this eyesore blue, let's change it back to black. Let's change this to white. Okay. And okay, let's try this again. So this is what we know. Okay. We can take this equation. Oh, I'm writing in black. This equation, which is a fundamental kinematics equation, to solve for v squared. Okay, in this case, this is just an indication of the final velocity in whichever direction. In this case, what we can do is use our y half of the values in order to solve for the y final velocity. Okay, so we know that, let's just plug in the values, okay? So we don't know this value, okay? We know that this value is 0, v naught is 0 in the y direction, so 0 squared is just 0. The acceleration is 9.8 meters per second squared, okay? And delta x is just the change in x, so x final minus x initial. I'm sorry, we're not dealing with x, we're actually dealing with y. So let me just change this equation. There we go. Let's go back. I believe it was 1.5, 1.25. Yeah, 1.25. So this would just look like 1.25 meters minus 0 meters. Okay. Once we simplify this using our calculator, we get that it is 2 times 9.8 times 1.25. that would be 24.5 meters per second. And this is meters per second. Sorry, maybe I shouldn't write it that way, but it's meters squared per second squared, because when you take meters times meters per second squared, well, you get meters squared over second squared. So this is what you get. Okay. Now, if you wrote the units, this would be a dead giveaway that you are not done yet. If you didn't write units, or you just thought it was meters per second, well then you probably wouldn't catch this, but you need to square root both sides because you have vy squared on this half, and so you have to square it if you want vy. Sorry, not square it, square root it. So if we square root 24.5, we should get 4.9497, and I'm just kind of taking sig figs kind of lightly here, but we will consider sig figs at the very end. So you should get something like that, 4.950 or 497 meters per second. Okay. So this is important because what this allows us to do is to go back over here and erase this and replace it and update it. Okay, so this should be 4.9, I'm just going to round it, 950, just so it fits on the screen, meters per second. Okay, and with these values we can actually solve for time. So let's come back here. Okay, let me just do this. Well, not with white. Here we go. Okay. And now let's give this another shot. So we can use this equation to solve for time, because we know this value, we know this value, and we know this value. Once again, we can't mix and match the x's and the y's. We have to consider the values from only one half, and we're going to use the y half because this has data that will not result in a non-zero value, or it'll compute, in other words. So 4.950 is equal to 0 plus 9.8, yeah, and then t. Okay, so we're going to divide both sides. Well, this, okay, if you really want me to do it, that just goes away because it's plus 0. What we can do here is divide both sides by 9.8. Okay, and we should get that t is equal to 0.505 seconds. Okay, now what we can do here then, since we found time, time is interesting because it is the only thing shared between the x and the y halves. So what this actually allows us to do is substitute t over here and t on the x side with 0.505 seconds on both sides. Okay, with this information we can actually solve for x using the final kinematics equation, which is x, or really any position variable, x is equal to x naught plus v naught t plus 1/2 a t squared. Okay, I did a pretty shoddy job right there. Don't want that to get confused as if it were in the denominator. Now this is in the top, a t squared. Okay, and in this case we actually can use the x variables because that's what's going to allow us to solve for x, which is in the end what we're looking for to find how far this ball goes. So we just have to plug in values, and x is equal to, well, x naught was 0, so that goes away. V naught is 1.0 meters per second, and time, as we just solved from the y half, is 0.505 seconds. Okay, and I'm not even going to bother to put the plus 1/2 at squared because acceleration is 0. So what is that going to do? It's going to turn this entire term into 0. So that means x is equal to, well, 1 times 0.505 is just 0.505 meters. Okay, and now before we box our answer, let's go back to the original problem and notice sig figs. Okay, so we're going to have 2 sig figs because it's restricted by the 2 sig figs in 1.0 meters per second. So this just simplifies to 0.51 meters. And that's the final answer.